Hey guys, BuildZoid here, and today we're doing another video about the Probinator results. This time we're focusing on the Gigabyte motherboards, so, you know, Z390 Aorus Master, Z370 SOC LN2, Z370 Gaming 7. This is not a retail board, you can't buy this, so, you know, I'm kind of happy that it's not performing, like, ridiculously well, because if it was, then it'd be a real shame that you couldn't, like, that Gigabyte never decided to sell one of those. Anyway, Z370 Gaming 7, Z390 Aorus Pro, Z390i Aorus Pro, and of course I have the dark in this this data chart here because I use the dark as my ruler. Since the dark is by far the best motherboard I tested, so it makes sense to just basically do all comparisons as a case of how close can you get to the performance of the dark, right? Like, so yeah, it's a very expensive ruler as it is a $500 Z390 board, but it is the best. So, you know, it's just like how close can you get to the best without spending insane amounts of money, I think is a reasonable way to rate motherboards. Though the thing is like the results I'm seeing here really make me wonder about, like, I really wish I had a more of a selection of motherboards for, you know, other brands like, say, Asus, because for Asus I only have the Gene, which I think is a real shame because I'd really like to see how, say, the like Asus has that 4-phase. What is it? Yeah, like the Asus 4-phase that they run for, like, the Hero, the Code, the Formula. I'd really like to see how that 4-phase does, because that actually uses, like, the Gene is on a ASP1405 voltage controller, whereas the other boards, they're on an ASP1400, I think. And the 14, like, there's the controller that the Hero and the other boards use is actually, like, that's a cheaper, worse VRM controller. So it's like, so I'm really wondering how that actually ends up, because it's like, well, okay, so we have the Gene gets, like, pretty close to the performance of the dark. But then is it like, so is, like, there's not much space between, like, you know, the Gene and then, say, let's say Gigabyte's worst motherboard, which is the Z390 Aorus Pro. Right? Like, there's not much space between, like, the Gene and the Pro, where it's like, so, you know, is the Hero, like, because I assume the Hero is worse. Otherwise, why would you redesign like, why bother redesigning the VRM for the Gene? And then from the Gene, the next step up is the Apex, and the Apex actually has a significantly designed power delivery system as well. Like, there are some, like, the Apex can get away with doing some stuff that you can't do on normal ATX boards, because the Apex doesn't have an iGPU rail, and it's just like that could potentially make a pretty significant difference. So it's like, I'm really wondering is, like, well, can the Apex catch up to the dark? The Godlike from MSI could also have the same thing, where it's just like they can have the entire, like, their vCore power plane can be completely different, like, can go in places where normally it couldn't go because there's an iGPU power plane there. So yeah, I'm really wondering is, like, how, because the thing is, between the boards that I've tested, the differences aren't exactly huge. You know, we're taking a look at, like, at least in the minimums, we're seeing, like, a couple millivolts, like tens of millivolts differences, which is like that's large enough that going from board to board, you would actually notice that some boards overclock better, but it's not so much like, it's not so huge that it's like some massive, like, it's not a massive advantage, but it still does make me wonder is, like, so, you know, is, like, how does the Hero perform compared to the Gene? How does the Apex compare to the Gene? How does MSI's lineup perform? That's another thing, is because I have no idea. How do the ASRock boards perform, right? I only tested the Phantom, so yeah, I really wish I had more boards to compare against, not just the Gigabyte boards. But unfortunately for me, getting boards out of the other motherboard vendors is just like, it's not gonna happen. Well, MSI I think would be cool, but yeah, like ASRock, it's just like, yeah, I have to buy those. Asus, have to buy those. So yeah, that kind of sucks. Anyway, let's start going through these different boards. So good news, bad news. So bad news, Gigabyte, like the master really isn't exactly impressive in terms of its performance, especially if we compare it to the dark. So basically, you know, at minus 75% or minus 50%, or even minus, well, minus 25%, the dark just gets into, like, at minus 25%, the dark absolutely crushes everything. So I think this is straight up as good as it, yeah. That's about as good as the dark. Well, okay, it gets a little bit better down here. Oh, no, that's still 70. So basically what I'm looking at is like the gap between the average voltage versus the minimum voltage, right? So because that basically tells us like how close together can you keep the voltage regulation, right? So anyway, the dark, you know, you're looking at 1.41 versus 1.33, 1.39 versus 1.31. So those are both 80 millivolts. So in that 1.4 volts range, you know, 80 millivolts gap between between average voltage and minimum voltage for our 128K. So I'm just going to note that down. So 80 millivolts. And then at minus 25%, you know, we're looking at like like 70 millivolts. What the hell happened to that cell down there? So 80 millivolts and 70 millivolts is kind of like, so that's kind of our target for 128K. That's what you want, like, that's ideal. And then for Prime 95, we're looking at like 1.47 versus 1.41. So there we're looking at 40 millivolts, 40 millivolts, 40 millivolts, 30 millivolts, 30, 40, 30, yeah, so basically 30 to 40 or 30 millivolts, right? 40 to 30 millivolts is the okay, that looks ugly. So I'm just going to put it as 40 and 30. So if we look at the master from Gigabyte, we will notice that, you know, for 1.4 volts, which is like turbo LLC, which is not, like, that's relatively, like, that's roughly equivalent to like minus 50% on the dark. Also, with the Gigabyte boards, you have the DyeSense readings, and I did note them down because obviously I'm measuring on the outer corner of the CPU substrate. The DyeSense reading is obviously from like the actual, well, it's not like, you know, it's somewhere in the die of the CPU. So still, like, depending on where you would measure, you would still get like lower voltages still. Like, I assume if you went like deep into some part of the CPU core while you're running AVX, like there might be some area which is running really low voltage compared to the rest, but still, yeah, this is like as accurate as your voltage readings are going to get. Like, this is what the load line is actually set against, which is why if you have ultra extreme, you get 1.4 volts with 1.4 volts set. So anyway, we can see that there's like a 60 millivolt gap there, 70 millivolt gap there, 70 millivolt gap there. And this holds true across most boards. So, you know, here we have a 60 millivolt gap, 60, and the gap shrinks at lower currents. So as the voltage goes down, the gap between the DyeSense and the average voltage measured on the corner of the substrate gets smaller. So yeah, there's a there's some resistance to the substrate of the CPU. So obviously that screws up the measurements a bit, but it is consistent. So it's like basically all boards are somewhere in that 60 to 70 millivolt range, right? Like this one here, we have 70, 70, 60, 70, 7, what, no, 70, 60, 60, 60, I can't do math in my head, still 60, and 50, right? And then we have here, we have 60, 50. Okay, so that's a bit of an anomaly right there. So we have a 50, 40, and then a 30. So for some reason, these are like not, yeah, so those are a bit anomalous right there, but other than that, most of the boards, like, you're looking at that, like, especially, like, basically, if we're reading 1.4-ish volts average, then we're probably getting around 1.35, 1.34, right? Like, something in that range on the actual core itself. So that's actually, yeah, if we're reading 1.4, we're measuring about, like, the core is getting about 1.34. So that, like, it is relatively consistent. So anyway, let's take a look at the master. So 1.4 volts, we can't really, on the dark, you know, that might be like 1.39 is the closest equivalent, which would be that minus 50%. 1.43 versus 1.36. So that's a 70 millivolt gap to the minimum, which is, you know, 30 to 40 millivolts worse than what the dark does. Yeah. Does this improve? Yes, you can get a 60 millivolt gap if you run, well, actually no, that's extreme LLC, so that's not fair. Turbo, that's 60. Yeah, sorry, I was reading the wrong row. Damn it. Anyway, so yeah, that's 60 millivolts. And then here we have 40 millivolts. So at high LLC, it improves significantly. The thing is also at high LLC, the voltage is a lot lower. I really wish Gigabyte had a high plus setting for their LLC because there's no middle ground. Like, right, this is an 80 millivolt jump. And then going upwards, right, this is a 40 millivolt gap. That's a 20 millivolt gap. Then it's 80. And it's just like, yeah, so if you're overclocking on a Gigabyte board, you're probably going to be running turbo LLC because on high, you're going to have to set your voltage like 80 millivolts higher to get the same voltage, right? So if you, like, I wouldn't let my CPU idle on 1.48 volts. Like, I just wouldn't. Because the thing is, if you ran, because here's the thing. The load line does not take into consideration how many cores are loaded. And how hard are the cores loaded. It just takes how much current is the entire chip pulling at the same time into consideration. So if you set like, 1.48 volts with high LLC, and then you just hammer 2 cores with AVX, it's not really going to pull a ton of current. Like, most of the chip is not going to be pulling any power. So you're going to be shoving a ton of voltage into 2 cores. And yeah, I would not feel comfortable doing that. Like, I'm pretty sure you would just, like, you would end up degrading those 2 cores while the rest of the chip was fine. So that's kind of the reason why it's like there's definitely, like, there's considerations to be made with the whole, I'm going to set my voltage higher and then run a droopier load line, where it's just like at some point, you're going to be running so much voltage at like basically at sort of like standard, like there's going to be workloads where it's like you're going to be degrading just like parts of the chip instead of the whole thing. So I don't think, like, I wouldn't set above 1.45 volts personally. Like, I wouldn't let the chip ever idle on more than 1.45, because so yeah, that's kind of the thing. And anyway, so if you set like high LLC, it droops really, really hard. It does improve your minimums, but if you look at like minimums in 128K, they don't really change that much. I mean, we're going from 1.33 to 1.24, so that's a 90 millivolt. That's 90 millivolts instead of 110, right? We're going from 1.4 to 1.29, and this, like, I'm actually pretty upset with that. So that's like 30, 40 millivolts worse than the kind of performance you could get out of the dark. So yeah, that is, like, the thing is, I don't think you would, like, from a power consumption perspective, it's not a huge deal, right? Because it would be like the difference between, so, because the thing is obviously this is after droop voltage is where you want to look at your power difference. So on the dark, let's say we were running, I don't know, 1.39, right? And then on this board, we would need to run 40 millivolts more than that. So we'd be running like 1.43 average. And it's just like, it's just 2.8%, right? And if we square that, we get about 6%. So you'd get more, maybe like 6% more heat output for the same overclock on the master, because the master just is so very, like, because the master has worse minimums. And I still need to, like, validate this, because one of the big issues with trying to compare minimum voltage versus max overclock on motherboards is that the LLCs do not match up, and the voltage readings are inaccurate, right? So I'm really glad that the average from the Probinator doesn't differ too much from the DyeSense across motherboards, because it's like, I know for a fact that we're within... like, I can go board to board, and as long as, if the Probinator says it's 1.4 volts, then the core is probably at 1.3 to 1, at around 1.34, right? Plus minus a couple millivolts. And actually, I could make that more accurate if by checking with a because the thing is, like, I'm using the average reading from the oscilloscope. Like, I could just use a multimeter to check as well, to get a few more digits. Actually, no, I should just use I know what I'll do. When I do the voltage normal, like minimum voltage versus max overclock testing with the Probinator, because I've not gotten around to doing that because that's super time intensive and I don't want to do it on all of the different motherboards. So what I'm going to be, and right now I'm thinking I'm going to test like the master, I'm going to test the gene, the dark, because the dark just looks like it should crush everything. And I'm also going to test the gaming edge because I really like the thing with the gaming edge board from MSI is just like I'm really like I like that board a lot for its memory overclocking, and its VRM thermals aren't as bad as they could be, especially considering that when I was doing VRM thermals on the Phantom Gaming, I didn't realize there was such a massive gap in the load line settings of the gaming edge and the Phantom Gaming. And the Phantom Gaming, like, I was testing, I think, at level 2 LLC, and that board was still needed a fan. So for me, it's like, okay, well, they both need airflow, so at that point, you may as well go with the one that has better memory overclocking support, right? Anyway, so yeah, when I do that, it's just like because the way I had this set up is like basically when the way I had the scope set up for measurements was it chops off some of the digits. So I can actually redo, like I should do some dye-sense validations again with the oscilloscope. And actually I should probably also, well, no, I'm not allowed to do it on some boards. But on some boards I am allowed to just connect directly to the dye-sense, well, the boards that I own, I can modify to as much as I want. So I can get dye-sense readings for a lot more boards. So when I'm going to be doing that, then I'm going to be I'm going to have this in more accuracy with not rounded to the nearest 10 millivolts, right? So anyway, but usually the problem is like you try to do comparisons and like the Phantom Gaming actually reports much higher voltage than it should because there's no way to get dye sense readings on that board. And I think the MSI board is even worse about it, where it like reports even more. Like I think out of all of the boards, the MSI board might have a voltage set, like its Super IO voltage readings are even worse than everybody else's. So it's just like the voltage readings are just completely all over the place between the boards. And it means that if you try to do minimum voltage comparisons, they're useless because you're measuring different things on every single motherboard. So yeah, and it also takes a ton of time. So a ton of time to like, you also need to figure out a stress test where it's like, I'm going to probably do a mix of like 16K and 128K, where it's going to be like, has to pass 10 minutes of, or 10 minutes is forever. Because if it's 10 minutes 128K and 10 minutes 16K, that's going to be like at least 20 minutes per board. No, it's going to be like an hour per board to get a oh my God. I hate this kind of thing. See, the funny thing is you can't do minimum voltage for Cinebench because Cinebench is really easy. Like, Cinebench is not a real stress test. Not for the VRM. There's no, like, it doesn't cause any transients. It's about as, like, it's basically, it's almost as low noise as idle. Like, it is really not useful for testing. So, anyway, but, yeah, where was I going? So, that's kind of the thing. So in theory, you know, if I did the board versus board minimum voltage testing, you're probably going to be like, in theory, it should be like 40 millivolts in favor of the, well, 30 millivolts in favor of the dark against the master. So that would be like 1.43 volts here to hit the same clock as the dark would do it on 1.4 volts, assuming there's not something weird going on with the rounding, which would really be maybe like 5 millivolts at most. So it might be like 25 millivolts versus instead of 30, but still, so that should actually be a measurable difference. Also, you know, it's worth doing at like high LLC. The thing is, it's not worth doing like medium LLC is not worth running because if we look at high, right, that's 90 millivolts. That right there at medium is still 90 millivolts. Like this board just has 90 millivolts as sort of the, like the voltage will go down 90 millivolts. And I think at that point the VRM recovers, or like, I really wish I had a way to monitor the PWM signals of the phases while 128K was running because I have no idea what the voltage controller is doing. Like, there's a very good chance that, like, because the thing is, a lot of the, like, International Rectifier, Intersil, all of these different voltage controllers actually have transient response, like, they have sort of advanced PWM control schemes to deal with transients better. I'm not sure if you can actually, like 128K is such an inconsistent load that I am not sure if those are actually running while 128K is running. Like this well, like I might have found something that's basically a capacitor bank test, which would explain why the dark is crushing everything because it has the best capacitor configuration, right? And then, but like 16K, like here we actually have transients where it's like, okay, this is an actual, like this, you know, there's a transient. We can look at it and go like, okay, this is the VRM dealing with something, but this is just basically a mess. So that's another thing that I'm wondering about. This may very well be just a capacitor bank stress test and nothing else. And that's why, like, you know, that's why, like, the dark, even with all of its doublers, is absolutely crushing it. It's just like, yeah, it doesn't matter. The PWM isn't doing anything about it anyway. So, yeah, unfortunately, getting, you know, monitoring the PWM signals of well, the only way I could monitor the PWM of a board while also having the Probinator hooked up is, like, if I had a 3-phase motherboard, which is just, like, a three-phase I think that's pretty pointless. Like, I really think that's not worth doing because a 3-phase board, there's not going to be anything. Anyway, so yeah, so the master, you know, goes down to 1.29, and, you know, like worst case, like, you know, like it doesn't make sense to run extreme LLC because that just makes the performance. Actually, it doesn't really change it too much, right? 110. So extreme LLC might actually still improve your overclocking range. But it does increase your heat output, right? Because we pick up, well, actually, you pick up 20 millivolts in here, but like, the thing is, these are rounded values again. So, you know, this could be like 1.335, and this could be 1.364. And that's, you know, that's not the same thing as 1.36 versus 1.34. So that's kind of a concern there as well. Is just like, yeah, the rounding really does screw with some of these. But anyway, according to the oscilloscope, there's a 30 millivolt increase in average voltage, and minimum voltage only goes up 20 millivolts there. And here you actually only pick up 10, right? So like that's kind of the thing, is just like, yeah, it runs it's going to run quite a bit. It's going to run a bit hotter on 16K, but it really shouldn't be much more stable on 128K. So that's kind of the thing right there. Then, you know, if we go from here, well, you know, this is 60, that's still 60. So that's kind of like there's no difference with high LLC versus turbo LLC in a steady load. And in 128K, the difference isn't like the difference isn't particularly huge. Extreme LLC is definitely a bad idea though, because you pick up like 20 millivolts, maybe more of stability, but you pick up 40 millivolts more. Like you pick up 20 millivolts of minimum, 40 millivolts of load voltage. So it's just going to run way hotter than it absolutely needs to. Right. And the gap is 120 millivolts at that point. So yeah, I really need to do the, you know, minimum voltage versus max overclock testing soon. Because right now it's just like especially with boards like this, where it's just like there's not huge performance differences between one LLC and another LLC. The only thing that really changes a lot, which is why the peak to peak value keeps increasing, is the amount of overshoot you have. The undershoot doesn't really seem to care too much. Then if we look at the Z370 SOC LN2, I gotta say I kind of prefer. The turbo LLC on this is different, so, and I think I kind of, I mean, not really. Well, no, it's slightly better, right? Like, you get 100 millivolts here instead of 110 at this point. So, like, extreme LLC is equivalent to the turbo LLC they have on the master. Which is just like, I really, like, evidently they had a turbo step, you know, LLC at some point in time that wasn't quite so, wasn't quite so aggressive, but anyway, so, you know, that gives 1.38, so that's 100 millivolts there, so that would be like 20 millivolts worse than the dark in theory. So we'd have to set like, I don't know, yeah, we'd have to set like 1.43, I think, because at 1.4 volts set, the dark goes down to 1.39, so that's kind of the thing. It's, again, like the LLCs aren't perfectly matched up, but... so we have 100 millivolts there, and then down here we get 90 again. So it's kind of the thing, is like the SOC really, like, this kind of surprised me, because this right here is an 8-phase with no doublers. This is a doubled 12-phase, right? So it's an IR35201, then there's a bunch of IR3599s, then you have a bunch of IR3553s. This is an IR35201 with a bunch of IR3553s, no doublers at all. And so I was really kind of hoping this would do a lot better than it does, but no, no, it doesn't. It's basically like, it's basically, the same performance as the Master. So I'm kind of sad about that, but at the same time, I guess, like it's a good, well, I don't know. I was hoping for more out of the SOC, but, like it's still only like a 20 millivolts versus, it's a 20 millivolt difference against the dark. So not really a huge difference at all. Like it stays 20 because, like if you run the dark on minus 25%, then it goes down to that 70 millivolt range. So it's not really fair to compare like, oh, well, what if you run it on high? Then it's only 70, then it's only 90 millivolts against, the 80 here, but it's like, that's way droopier, right? So that's kind of the thing there. Anyway, so the SOC LN2 really, like, I was really hoping it would blow me away. It didn't, so that's kind of a shame. Then we have the Gigabyte Z370 Gaming 7. I was worried about this board. I was worried the Gaming 7 would suck because I tested a motherboard with a different Gigabyte motherboard with an Intersil Vrm where we were seeing like massive peak-to-peak values. Unfortunately, those measurements were taken from the back of the CPU socket. So I don't know if it was an overshoot problem or if it was an undershoot problem. Judging by the Aorus Pro, I'm going to say it's an overshoot problem because, okay, like it's not quite so, it's not as great as the Master on the undershoot, right? It's 1.28 against 1.4. So it loses to the Master by 10 millivolts, which again is like, this is why you don't see significant differences upgrading motherboards in terms of overclocking capability. I guess if you took a CPU from the Pro and stuck it on the dark, you might be like, whoa, it overclocks what, 30 millivolts better? 40. 40 millivolts better. It's like, so you might notice a big difference if you go from like that's $180 board to a $500 board. And it's just like, nobody really does that. Nobody does that kind of comparison either. But anyway, so the Pro, the Pro, really bad peak to peak results, but most of that's just piles and piles of overshoot. And the overshoot doesn't affect your stability. And also, the 1.61 volts there looks high, but it's ultra extreme LLC. So you shouldn't be running that anyway. Extreme LLC is 1.54 volts. And the other thing is with the overshoot is not an electromigration hazard. It's a oxide breakdown hazard, but I'm not sure what voltage you need to be at to get oxide breakdown. So, and I think because the thing is, like, electromigration is the current flowing through the CPU eroding all of the metal layers. And that's bad. So that gets worse with more current, and it gets worse with higher temperatures. Oxide breakdown, on the other hand, is basically when you apply so much voltage to some part of, say, a MOSFET that the voltage just blows through the insulator, which, let's say the gate oxide, right? Which the gate oxide basically separates the gate of the MOSFET from the channel, and it's just like, yeah, if you put a hole in that, that's bad because you're not supposed to have current flowing through the gate of your transistor into the channel of the transistor or in any other direction. Like, there shouldn't be current flow between those two things. So, yeah, but the thing is, there's like a minimum voltage level that you need to reach for that to actually be a problem. And I don't know what that voltage level is, and I don't think it's 1.61 volts. On the basis that you can literally apply, like, you can bench CPUs at ambient on 1.6 volts and they'll not up and die instantly. Like, it takes a while before they die at 1.6 volts. So, because of that, I'm going to say that's not like an instantaneous death hazard. If it was maybe like 2 volts or something, then I'd be like, okay, this is probably going to blow the chip up. But I don't think, like, it's not an electromigration hazard. It might, I don't think it's high enough to be a degradation hazard in any other way either. But yeah, it does blow up the peak-to-peak values of the Pro quite significantly. And I think, like, so basically, I was really worried because there's another motherboard from Gigabyte that uses the same VRM as the Pro does, where it's like, I saw the same thing where the peak values were absolutely insane, but those were back of socket measurements, so the minimums are not comparable across various motherboards, right? Again, this is the great thing about the Probinator, just being like, there's a fixed resistance between where I'm measuring and versus where, versus the CPU die, so my minimums are comparable. not 100%, right? There's seems to be like 10 millivolts of error between some of the boards, because like this is 70, whereas on the master, well, no, that's still 70, right? Like that's 70 millivolts, 70 millivolts. So this measurement right here is very much going to be comparable to that measurement right there. And you really shouldn't use Ultra Extreme LLC on the Pro, because it really can't deal with it. Like there's a large amount of undershoot at that point. Right? But Extreme LLC, you know, is actually like, this is the funny thing. The Extreme LLC is about like the closest thing you have to sort of turbo on the master. But if you want actually like the best kind of performance, because here you're looking at 120 millivolts, whereas down here you're looking at 110. In terms of undershoot performance, it's turbo versus turbo are equivalent. So that's kind of that. Also, the high LLC seems to be, yeah, like the high LLC is a bit higher, right? Because 1.34 versus 1.33 there. And 1.24 versus 1.24 there. So yeah, again, and here the gap between these two is larger again. So basically, I've seen a VRM that was like intersil with doublers from Gigabyte before, where it was like, okay, I had huge peak to peak. So when I was getting ready to test the Gaming 7, I was like, oh my god, I'm going to see like 300 plus millivolts peak to peak when you max out the LLC. But no, the Gaming 7 does actually pretty well. It does it actually matches the master. So the only real thing you can complain about on the Gaming 7's VRM is the VRM cooling system, which sucks. Like that board's VRM runs really damn hot. It has no business doing that, considering that it's an 8-phase using a bunch of 60 amp smart power stages from Intersil. Like Gigabyte really screwed up with the cooling system on that board. But hey, the transient response isn't really anything worse than anything else they put out, so that's a good thing. And really, like, what I find interesting is that actually the Extreme LLC on that board is not, like, I was expecting the Extreme LLC to have problems, but no, it's actually not that extreme at all. It's pretty droopy, right? Like, it's about as droopy as Turbo on the Master. Like, it's basically the same amount of droop as the Turbo on Master. So, yeah, that's kind of... Like, I'm surprised that there's these there's these big differences between the boards. High on this board is an absolute disaster in terms of how much, like here it's an 80 millivolt gap, and here it's 90. So it's just like, yeah, from bad to worse. This really needs a high plus setting, in my opinion. Like, there should be a mid step between high and turbo for this board. And again, it's just 90 millivolts peak to peak. So again, this should be about 20 millivolts worse on average than the dark. So, yeah, which again, 20 millivolts is not that significant difference. And again, rounding, there's rounding concerns. So it could be as little as 10 millivolts difference. And at most, it could be as much as 30. So, yeah. Now, funnily enough, I've kind of not mentioned this, but the ITX from Gigabyte actually outperforms all of their ATX boards, which I don't think it's a doubler thing. And I don't think it's a doubler thing because if it was a doubler thing, this would be beating everything else on the charts. And the dark wouldn't beat everything ever, right? Like the dark wouldn't be beating everything I ever tested if doublers made your undershoot worse or significantly worse because, well, this has a bunch of doublers in it. But then it's like, yeah, this is a 6-phase, no doublers. Like, it's very similar sort of in terms of control scheme to the 8-phase of the... Like, actually, it's really similar to the 8-phase of the Z370 SOC, right? Because, like, the Z370 SOC VRM can basically be described as the VRM off the ITX with 2 more phases. Like, that's the only thing. It's the same controllers, same power stages, same inductors. And yet, the ITX has a 20 millivolt advantage over the SOC. So, yeah, and I think most of that is down to the shorter power plane. Like, I really think it's just a shorter power plane. It might also be down to the layer count. I don't know if that ITX is an 8 or a 6, as in 8 layers or 6 layers. And obviously because here's the thing, if you have a shorter power plane, that's less resistance, that's less power, like you have less resistance, you have less inductance in the power plane. If you have a power plane with more layers, again, less inductance, less resistance, better transient response. So that is kind of the only 2 things I can really see where it's like, okay, there's a big difference between the ITX and the SOC is just like how close is the VRM to the actual CPU socket. And then the master is just like, I actually have no idea why the master is not doing a lot better than it is. It could again be just a distance thing. Gaming 7 is like, yeah, it's really like, I'm really surprised that the ITX does so well, but it does. Unfortunately, also runs incredibly hot. So yeah, I'm going to try to test, well, I wish, there's not really a great way for me to test my theory about the like capacitor proximity to the CPU socket, because I can't modify the actual power plane of the boards. Like I can't add capacitor mounts closer to the CPU socket so that I could move the entire capacitor bank, you know, from the, because the way Gigabyte, like let's go to here, right? Like basically, I think, because if we look at these boards, oops, wrong layer. So here's the ITX, right? And the ITX has these 8 capacitors for its bulk capacitance for vCore. If we compare it to the master has all of this for its vCore. So this actually has more capacitance. This is 10 bulk capacitors. They're the same brand. They're Nichicon FP series. So, you know, I assume the ESR and ESL of these capacitors is going to be the same. And the only real difference between these two boards is like, these capacitors are in line with the mounting holes. These are like significant, like quite significantly ahead of them, right? So the VRM of the ITX is really jammed up against the socket. And it's also worth noting that if you look at like, say, Asus motherboards or the Dark, right, the bulk capacitor bank basically goes all the way up to the socket. Like what Asus likes to do with their motherboards is they actually have a set of capacitors that goes right here. And that very well could be part of why the Gene actually performs so well, right? Is just like, where are the capacitors located? Because the thing is, during a transient, especially like, you know, CPU decides to suddenly start pulling a bunch of current out of nowhere, you're basically like the resistance of the power plane basically reduces the effectiveness of all of your capacitors, because you're trying to, all of that current that the CPU suddenly wants, it's trying to grab it from a capacitor bank that's further away. And that reduces the effectiveness of the capacitors. So that's my theory on why the ITX is performing so well, because there's really nothing else. Like if we look at the back of the board, right? Like again, we just have these little multi-layer ceramics that are in the vCore of the ITX are closer to the CPU socket than they are on the master, right? Like there's a bigger gap between these and the capacitor legs themselves, I think. Kind of looks like it to me that way anyway. So basically, I think it really is just like a distance thing, because the actual capacitor configuration in the socket is the same, because the vCore is all of this. This down here is like VCCIO, VCCSA. This is VMEM, and this is iGPU power. And on the master, you know, it's the same thing. This is all vCore. And then iGPU, VCCSA, VCCIO, memory power, iGPU. So, like, that's the same on both of them. And the master has more bulk capacitance. It uses 300 nanohenry inductors, same as this does. It uses a bunch of 3553 power stages, same as the ITX does. And it's just like, yeah, the only thing I can think of that would make the difference is like these caps are closer to the socket than on the master. There might be more layers on this board as well. That could be another difference. So that kind of makes me wish I had the Z390 Extreme, because that's an 8-layer PCB. And if it's a layer thing, then the Extreme should beat the Master. Or, you know, if the Extreme gets the same performance as the Master, then it's like, okay, it's not a layer thing. It probably is just a capacitor location thing. At that point. But layers should, like, the thing is, if you put the capacitors closer, you're just reducing the inductance and the resistance. So if you just had more layers, that would do this, that would effectively make the same, like, should make the same effect potentially, without having to actually shift the capacitors closer. So anyway, that's kind of like, yeah, I'm not sure why the ITX performs so well, but that's kind of the only thing I can think of, you know, because, yeah, it's just like the capacitors are closer, and there's nothing else I can really go and say like, yeah, I can see that there's this big difference in the design of the two boards, where it's like, yeah, this should do it. Because the doublers, if it was the doublers, then, you know, the Z370 SOC right here should be beating the ITX as well, except it's not. And admittedly, the Z370 SOC does not use the same socket capacitor configuration. And in fact, I don't know how it's laid out here. I think might be this for vCore. because there should be a cap out here for memory power. So, and it actually kind of looks like that would be this one, because that one's out of line with the rest of these. So there is a difference there, because these are 0603 capacitors, and those on the SoC, those are 0805s. But the other thing is, like, this is a real 8-phase. It uses 300 nanohenry inductors. It uses a different brand of capacitor, which might also have an effect. Like, maybe these have a slightly higher ESR or slightly higher ESL, and so it's just like they're less effective than the ones on the ITX. But this thing also loses to the ITX, and, you know, the main difference I can notice here is gap. Like, actually, if anything, I think that's the biggest gap. Yeah. Yeah, I'm pretty sure that's the biggest gap, is the Z370 has them further away. And this one, the capacitors for VCore are like 1, 2, 3, 4, 5, 6, 7, 8. Those. These two down here are VCCIO and VCCSA. So this is all VCore. And yes, this one's just kind of hanging out in the corner for some reason. I really think they should have put, like, there. But, like, done the Asus thing, you know, put 2 rows of capacitors towards the CPU, but anyway, because I think that might actually, like, work. Because I don't think Asus does that for aesthetic reasons, right? Like, I think most people would agree this is a cleaner looking motherboard layout, but then it's like so I don't know why. Like, I can't think of another reason for Asus to put those capacitors where they put them, other than, like, it actually helps performance, because otherwise, why don't you just put them in a row, right? Like, yeah, like, it doesn't really, like, I don't think the pick and place machine particularly cares if they're here or there, right? So that's kind of the thing. But yeah, so the Z370 SoC loses. And the Z370 SoC also has basically the same transient response performance as the Gaming 7, and the Gaming 7 uses a bunch of doublers. But it also uses FP series, like Nichicon FP series capacitors, 150 nanohenry inductors, which I think is why this might not be like the Pro has a ton of overshoot issues. This doesn't. I think it might be down to the inductors, because, like, if we look at how many capacitors this has the same sort of, like, it's it's these. Actually, no, it's all of them. So it's like 1, 2, 3, 4, 5, 6, 7, 8, 9. Wait a minute. No, it isn't. Yeah, no, it isn't. That's iGPU up there. These. So, yeah, that's the thing. So, the Z370 Gaming 7 has the same performance as this as well. So, it's just like, okay, I'm not really sure how the ITX is beating all the other boards. But yeah, this does use a bunch of doublers, and it also actually has a pretty, like I think this is another one of those boards with a bigger gap between the CPU socket and the actual capacitors. But then it's just like, well, lower inductance, so major differences. 0805 capacitors, again, it seems like basically for Z390, Gigabyte redesigned their CPU socket capacitor configuration. So they went from all these 0805s to a bunch of 0603s. This might actually be less capacitance than this. I'm not sure, because you can get 47s in this package size, but only, like, the highest you can get for these, I think, is 22. So yeah, I'm not sure how that works out. This could be maybe a little bit more. Like, I'm really not sure how they compare. Anyway, the Z390 Pro uses the same capacitor configuration as, like, the Master, as well as the ITX. Then we have all of these capacitors right here. I think these two are woefully out of position. Like, this is totally the wrong place to have those, but sure. Like, again, I just shift them that way. Anyway, this board is a 4-layer PCB. So I think that might be part of why this has more undershoot than, say, the Master, is just like, because the capacitor, like, this has doublers, it uses power stages, not discrete MOSFETs, it uses 300 nanohenry inductors, it has the same multi-layer ceramic configuration in the socket, and then it's just like 1, 2, 3, 4, 5, 6, 7, 8, 9, I think it's 10, yeah, it's 10. Because you can actually see that there's a split in the power plane right there, so this is all VCore, right? So we have, like, 10 bulk capacitors, and then it's just like, okay, this is a 4-layer, that's a 6-layer, this has slightly less undershoot. I'd say it's probably down to the layer count at that point. Though there are also differences, like this seems to have less of the multi-layer ceramics in the actual VCore VRM itself. I think it's like these for that, like those. right there. So if we compare that to the master, then obviously like the master has like one, two of them together, and these guys up here, those, and that one. So it's like there's some pretty major differences. The ITX also has those. It has less of them, but they're jammed closer to the socket again, just because well, these are like, you know, far away from the hole, and these are basically in line with it. So that gives you an idea of just how much closer they are jammed to the CPU socket. It would also explain why I say the Z390 Phantom Gaming ITX from ASRock is also doing pretty well in terms of transient response, but it doesn't have, like, you know, it actually has even less bulk capacitance than some of the Gigabyte boards here. Like, that one's a 6 capacitor configuration. It actually has the least bulk capacitance out of any board I tested. And it's just like, why is that doing so well? So, yeah, like, the thing is, right now I have a lot of questions, not really a lot of answers, because it's just like all of these boards perform very similarly. None of them is particularly amazing. Like, none of them has me like particularly blown away. I will be modifying some of them. I've already decided that, like, I'm modifying the master because I have 2 masters, so you know that gives me the freedom to kind of go crazy on one of them. Also, I like basically I have, like, I want to keep one of the masters because it has really good memory overclocking. So I want to keep, like, 4 DIMM memory configurations. It's absolutely great at them. So I want to keep it for that reason. And so I want to have, like, if I'm going to make a master better, then it's going to be my master, right? It's going to stay in my collection. It's the best master ever made. So yeah, and actually already, I already modified the board before shooting this video. It ended up with an extra capacitor here. I added just a bunch of multi-layer ceramics here, and then I decided this gap is huge, so there's actually like 2 caps and then another one, and then 2 more, and another one, and 2 more, and another. Like, I have like 3 capacitors added, like, so like 9 extra capacitors. 4 of them are like 47 microfarads, so it's like I added quite a bit of capacitance to the socket. I'm kind of hoping that actually improves the minimums, because I think for the minimums, the biggest priority, like the overshoot happens from the inductors to the capacitors. The undershoot happens from the CPU die to the VRM, right? Like, you need to, like, I'm kind of just trying to think about, like, sort of the direction in which the currents are happening, because on the overshoot is basically energy stored in the inductors having nowhere to go, so it's being dumped into the power plane, and it's just like, where, like, the more capacitance you have, the more you can, you know, suppress the voltage spike from that. The undershoot is a case of the CPU die suddenly trying to pull in a bunch of current, and it's not there. Right, so you basically want to get the capacitors as close to the die as possible. And I'm not going to modify the CPU because it would throw out, like, it would throw off my measurements, right? Something I do want to toy with in the future is modify the actual CPU substrate. Because remember the 7740X? I think the number one reason why a 7740X blows a 7700K out of the water in terms of overclocking is because the 7740X gets to take advantage of the much larger number of V-core pins in an LGA2066 socket, and also because the 7740X has way more capacitors on its substrate. Like, it is a ridiculous difference looking at like a 7740X versus a 7700K. Honestly, it makes me wish that we had like a 9940X or something. Actually, no, we have a 9940X. It's a 14 core, but like an 8700K. So like an 8740X. Yeah, 8740X for X299. I think that would be a really cool CPU to have. So like 6 cores, because I think like with the 7740X, like, that's a quad core. I don't think it can really take advantage of the improved power delivery of X290 of an X299 motherboard. But with like an 8700K or a 9900K, like, those chips pull a lot of current. I think it would be really cool if you could get those in like a basically upgraded power delivery package for X299. It's just like, yeah, but you can't, so that kind of sucks. It's a shame. But anyway, yeah, so basically I'm messing with the master. I'm going to be messing with maybe like adding capacitors first here and then adding them like further away just to, you know, mess around with the distance thing. Also, I'm going to be modifying the Z370 SOC LN2 just because, well, it's mine. It's never going to leave my hands. Like, there's no, like, it's an SOC LN2. Like, I'm not getting rid of this board probably ever. unless it's like unless I'm extremely desperate, I am not letting this board go because that is an LN2 board from Gigabyte. Those are rare and they're special and they don't make a lot of them and it's mine. And so I'm sad that they don't actually sell them, but since I have one, it's not leaving my it's not leaving. It's not leaving my hands. If it dies, it'll become a wall ornament. It is not leaving. So yeah, I'm thinking I'll modify this thing as well. And with this board, I mean, look at all this space right here. Look at all this, look at all this space over here. Unfortunately, I can't really stack capacitors on the back of a motherboard because, well, AMD motherboards are fine, but Intel motherboards, you can't really stack capacitors on the back of the socket because hold down brackets go like that, and then you're screwed, right? Like if they're taller than this metal plate here, yeah, you're screwed. So all this space over here, all this space over there. I kind of wish that, you know, like if you look at the Z3, the Maximus 11 Gene, there's a bunch of multi-layer ceramics just like going towards the CPU socket, like in this area. Yeah, this board doesn't have that. I really wish that was present because I'm pretty sure the V-core pins are actually connecting directly to the top V-core layer, right? Like this right here is all going to be a V-core fill. So like, you know, I'm not sure how vias work out for your resistance and inductance, but I'd assume it's worse than just having having the capacitors on the same layer as where the pins actually connect. So yeah, it's a shame, but hey, like, you know, I guess like you need to give Asus some credit with all of the marketing they do about transient response, whereas it's like their boards actually look like they're trying to do something about it, where it's just like you have some pretty interesting locations for multi-layer ceramics on Asus boards. Like they will jam them, like, well, yeah, like they'll jam them here, they'll jam them there. You know, anywhere there's space near the socket is just like, bam, extra capacitors. So yeah, anyway, on this board, it'll probably, like, I'll fill out this area as well. I'll just completely fill those two areas out. And then I want to experiment with maybe adding bulk capacitance only to, like, this area instead of, well, actually, no, I think it works out that, because the pins are in, like, right here-ish for V-core. So basically, the closest capacitors to that would be this one, this one, this one. So I want to experiment with, like, a proximity thing. If the distance thing is a thing, then it's just like, well, obviously a capacitor out here is going to be less effective than a capacitor right here. But I first need to like get a capacitance sizes that are big enough to make a difference in the first place. So that's going to be interesting to see if I can get any more performance out of that. I don't really want to work on the Z370 Gaming 7 because it doesn't, like, it performs similar to the Master unless if I get some crazy results out of the Master or the SOC. Then I guess I might do the Gaming 7 as well, just out of interest, and maybe the Z390 Pro. But like these two boards are very much boards like I have too many boards. These are probably gonna go soon, so that's kind of the thing. But I'm probably I might end up modifying them as well. It depends on how much time I have, right? So. Yeah, also it is worth noting, so yeah, Z370 had the 0805s in the socket, whereas Z390 went to 0603s. Not sure how much of a difference that actually makes. Like, in theory, the 0603s are going to be better at, like, higher frequency switching noise from the CPU, but at the same time, I'm wondering, one thing you have to consider is, like, does that high frequency switching noise ever make it past the socket? Right? Like, that's the thing, is like there's the CPU socket. So it's like you could, you know, go for some like 0402s or even 0201 little multi-layer ceramics like you see on the back of a lot of high-end, like on GPUs, right? Like look at the back of a GPU core and it's just like compared to what you see on motherboards, it's just like it's a completely different design for the filters. And it's just like, but that only works because GPUs are BGA and not LGA. If GPUs were LGA, you would not see that on the back of the GPU because it wouldn't bloody work. Like it wouldn't do anything because there's the connection would be blocking too much of the switching noise itself. So yeah, that's one thing I'm wondering is like if this actually makes a meaningful difference, because from my testing, it really doesn't seem to make a meaningful difference, right? Like Z370 Gaming 7, 1.4 volts, 1.29. Z390 Aorus Master, 1.4 volts, 1.29. And you might be like, but there's more overshoot. Well, that's because the Z370 Gaming 7 that's probably because the Gaming 7 has 2 bulk capacitors less. So that's part of it as well. So yeah, it's interesting to like. I'm really interested to like, basically I still have more work to do, but this is kind of my thoughts on the Z390 Gigabyte boards, where it's just like, yeah, it makes sense that Turbo LLC is like the favored LLC because high is really droopy, and it really doesn't give you a big advantage, right? It's like 90 millivolts versus well, I really need to test that. The thing is, I'm probably going to have to test that where it's like, instead of trying to hit, because getting high to hit 1 point like this right here, I'd need to set like 1.49 volts set voltage to get high to match the amount of voltage that we get on turbo. Like this high would be like 1.4. You might even have to set 1.5, right? Because like this isn't a, like, the droop isn't fixed. It isn't like high isn't set to like droop by 90 millivolts. No. It's set to droop this much per amount of like drop voltage by this much versus this much current, right? So if I set 1.49 and the current goes up by a large enough amount, I might still get like 1.39 instead of 1.4. So I think the way I'll actually do it is I'll get high to go up to like 1.35, and then I'll bring turbo down to 1.35. Or that, like, I'll basically have to match them at a lower voltage, not a higher voltage, because getting high to the really high voltages is just like, yeah, there's no way you're doing that. So yeah, and then in terms of the testing, I think I'm going to do 16K and 128K. I'm not sure for how long yet, because the thing is like, you could just do a stability pass, and also there's thermals. This is the really annoying thing with trying to do minimum voltage testing, is if you're doing testing and the water in your cooling system, like if the coolant heats up, I guess I should just get an air cooler for this. I have an air cooler. I can use an air cooler. Hell yeah, I'll just do it with an air cooler. So yeah, I have a Fantex PHTC14P, so I'll just use that. That should handle an 8700K fine if we're, drooping into the 1.3 volts range and not trying to run like 1.4. But yeah, that's kind of the thing, is like, the other concern is like, if you are using water cooling, then the temperature of the water loop is going to screw up your results. Because if the water is 5 degrees warmer, or if it's 10 degrees warmer, then like you're done. Like, the results are wrong. So you need a cooling system that saturates very, very quickly. Which is why I want to go with an air cooler, because a kilogram of copper, or which most air coolers aren't a kilogram of copper, they're, a mishmash of copper and aluminum. Like, a kilogram of some kind of metal is going to have far less thermal capacity than a kilogram of water ever will. So that's kind of why, and aluminum especially is kind of like, it's not as bad as people think it is for thermal mass, but it is significantly worse than copper. Like, it's a decent amount worse than copper. So yeah, if I use an air cooler, it shouldn't, like, the thermal saturation thing shouldn't be as much of a concern, hopefully. Yeah, because that's another thing, is like, if your water temperatures are going all over the place, invalid, like, and just like that, your results are wrong, because you're not testing in the same scenario. And it's really obvious if you're doing the testing on like a GPU or something, but on CPUs it's not quite so obvious, because like the frequency steps are so large. But on a GPU, you can actually like you can literally, a couple degrees is the difference between like finishing like say a 290X or something. A couple degrees is the difference between finishing, say, Firestrike at 1210 versus 1200 on the core at the same voltage, right? So like that's kind of the thing, is like, it is like, yeah, whereas on a CPU, your frequency steps are 100 megahertz. So it's just like, you're not going to notice that a very small change in stability. But if you're going for, fiddling with the voltage, then yeah, it's going to really screw it up. So yeah. That's kind of the concerns that go into this kind of like trying to do voltage comparisons is like, I know people have been doing them for ages and ages and ages, and my thoughts on it have always been like, you're just doing it wrong because like you need to control for so many variables. Anyway, so yeah, and also the room temperature. Oh, that's gonna be fun. I hate because like I have a pretty small room. Like the CPU running, I don't have AC, so the CPU running is actually a the CPU heating up the room is actually a concern for me. Oh, damn it. Oh no, I should just do it outside. Because the thing is, if you're outside, it can't heat up the air because there's so much of it. Anyway, no, that's not viable. That's not really an option. But anyway, I'll figure something out, and if I don't figure anything out, then I'll not do the testing, right? Because yeah. Anyway, hopefully this was somewhat interesting, and oh my god, this video is an hour. Oh well, I don't think anybody expected anything less than that. Yeah, basically, Gigabyte, like these are actually even worse than like the master is actually worse than the gene. So that's another thing is like I should compare against the gene. But the thing is at this point my gene is not like a reference, like it's not a stock gene anymore because I swapped all of the inductors and I'm not swapping it backwards because swapping inductors sucks to do and I'm really bad at it. But yeah, and I also have a Z390 Phantom Gaming ITX modified, so it's going to be interesting. Like, I can't wait to see, like, modded results, and then also the voltage matched results, and then minimum voltage versus frequency. I'm going to do minimum voltage versus frequency last, because that's, like, the biggest... Like that's the thing that is least likely to work correctly. Because everything else is just, like, we just see what we get at whatever settings I've standardized, right? Which is what this testing is right here. So... yeah, that's the end of the video. Another hour about the Probinator. But the thing is, this is a, like, this, you know, as small as the differences are, right? Because again, like, this is 80 millivolts, that's 110, that's 30 millivolts of difference. Not really a big one. So as small as the differences are, it's just like, this is a topic that is just ridiculously deep. The funny thing is 30 millivolts is also such a small difference that I don't think, like, I think that's why if you see, well, the other thing is, like, in extreme overclocking, all of the benchmarks we run, like, I can't think of one that's, like, particularly transient intensive. Like, Geekbench might be. So I might check that if, like, Geekbench like runs particularly inconsistent or something. But a lot of benchmarks, like Cinebench, just straight up not really, like, it's not a workout for the VRM. It's really stable. So yeah, I think, like, and also 30 millivolts is such a small difference that you may as well just run, like, you know, like you just droop down into the voltage you want anyway. So yeah, that's kind of the thing is, like, I don't think, like, looking at, like, because there's also the binning thing, so it's just like, unless somebody takes the same CPU and runs it on 3 different boards and the thermal paste application is exactly the same every time, like, looking at world records, not really a reliable way of gauging which motherboard's the best. Because a lot of, like, sometimes it's literally just a case of, like, well, if you bin enough CPUs, the garbage motherboard will still win, right? Unless it's, like, especially bad. So yeah, because it's a 30 millivolt difference between, like, the dark and the worst. Actually, no, it's like 40 millivolts between the dark and the worst board in the list, which that would be that right there, right? So yeah, which, like, that's not a very big difference. So that's kind of that. Anyway, yeah, so that's it for the video. Thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. I assume everybody found this really boring, or more like you're really annoyed that I haven't gone and done even more hours of testing. But the thing is, like, I want to take a break from probinating. Like, I love the Probinator, but I'm tired. I'm really tired of looking at oscilloscope measurements. Because I was doing this for like 3 or 4, like, I actually don't know how many days. I think I spent, like, yeah, I don't know. Like, I have literally no idea how much time went into just gathering all of this data for me to go and, like, yeah, this data makes me ask a lot more questions. Anyway, yeah. So thanks for, I'm repeating the outro. Sucks. You're used to this. Thanks for watching. Like, share, subscribe. Leave any comments, questions, suggestions down in the comment section below. And if you'd like to support what I do here with actually hardcore overclocking, I have a Patreon where you can support me directly. If you don't like Patreon, then, you know, there's also the AHOC Teespring store where there's shirts, stickers, posters. Those do help out with running the channel immensely. And yeah, if you'd like to check out, you know, either Patreon or Teespring to support the channel, that I would be, well, damn it. I didn't know where I was going with that. I'm bad at advertising my own merch. That's what we're getting at. And Patreon. Anyway, you get the idea. Everybody does this. So yeah, there. Links down in the description. If you want to help out the channel, then that's the way to do it. So yeah, that's it for the video. Thanks for watching, and goodbye.